Hi everyone, today we're talking about topic 5.5, the collision model. So we've already discussed this in 5.1, but there's a few different factors that affect rate. One is temperature, right? Increasing the temperature means an increase in the rate. Frequency of collisions, more collisions equal a higher rate. Orientation of molecules, in other words, molecules must collide with the correct orientation. Otherwise, no reaction will occur. And then lastly is the energy needed for the reactions to take place. In other words, the activation energy. For a reaction to occur, you need more energy than the activation energy. Otherwise, the reaction won't happen. Now, as I said, first, temperature. Generally, as the temperature increases, rate also increases. There are some examples where this doesn't happen, but we won't really be covering those. The rate constant is dependent on temperature, and so K will change at different temperatures. We won't talk about in this class the equation that actually governs this, but the only thing you need to know is that if T increases, generally, K will increase, which makes sense. The rate constant tells you how fast the reaction will go. The higher the rate constant, the faster the rate. So the higher the temperature, the faster the rate, the higher K will be. And the reason is because of higher kinetic energy. I said we're not going to talk too much about energy, but the reason behind this is technically kinetic energy. Particles are moving faster. If they move faster, they collide more often, and it means that they collide with a higher energy. So higher kinetic energy means higher rate constant. Frequency of collisions. Of course, the collision model is based on kinetic molecular theory, or KMT, which we talked about before. If you want a refresher on this, this was back in Unit 3 that we discussed the kinetic molecular theory. But they must react to collide. The more collisions there are, the more reactions, right? And so if you have a lot more collisions happening, you have a lot more reactions happening, and therefore your rate should go up. Generally, if there are more molecules, the reaction rate is faster. So if number of moles goes up, the rate will also go up. This is another way of basically saying that higher concentrations equal higher rate. This is, of course, there's a caveat to this, and that is zero order reactions do not show this effect, because increasing the number of particles or the number of moles or the concentration doesn't actually affect the rate. So for most reactions, higher concentration equals higher rate, but if you have specifically a zero order reaction, then the frequency of collisions isn't necessarily a factor. We've discussed this a little bit before, but this is just a reminder that orientation of molecules is also important. Oftentimes collisions happen without forming products, and that's because the molecules have to collide in the correct way. In this case, we're forming Cl2 in this top reaction. Here I have just Cl reacting with ClNO. In order for this reaction to happen, the two Cl's have to collide with each other to form Cl and NO. If the Cl collides with the oxygen part of the molecule, you end up getting no reaction. And lastly, activation energy is the minimum energy you actually need for a reaction to take place. We'll often call that the activation barrier. You'll also hear that term being used. It's, of course, a barrier because this is what prevents the reaction from going forward. But basically, we've seen this before in the context of a reaction coordinate. Here we have reactants. Here we have products, and this is energy, right? You need this amount of energy. So let's say this energy is actually 112 kilojoules per mole, right? Just throwing a number out there. If my reaction is given 150 kilojoules per mole of some form of energy, this reaction will happen. Now, it's an important thing to note here that this is completely independent of the energy of the reactants and products. So this is my energy. Let's say I actually have a reaction like this, where this energy barrier, this energy barrier here from the reactants up to this activation energy, let's say this is 200 kilojoules per mole. The products are at a higher energy than the reactants. That doesn't actually matter though. All that matters is that, let's say I have 250 kilojoules per mole of energy. This is more than activation. Therefore, even though the products are at higher energy, which can either mean, it's non-spontaneous, for example, if we're thinking about this in the context of delta G, if it's not spontaneous, even though it's not spontaneous, I have more than enough energy for the activation to happen, so the reaction will occur. Or in other words, the collisions are working. The point I'm trying to say here is that kinetics is separate from thermodynamics. So do not confuse the two together. Thermodynamics explains the energy of the reactants and products. Kinetics just tells you the amount of energy required for this reaction to occur, which is the activation energy. This was kind of our just refresher on collisions and just talking about the collision model in general. We'll talk about this a little bit more in class, but for now, that's all. Thanks, guys.